Hello, I'm Daniel Kinney, and this is the video for my project for Microprocessors A as well as data conversions. I created a whack-a-mole game. Pretty much a light comes on and you push the button for the corresponding light until the next light comes on and you push the button for that one, and you continue and score points until you run out of lives. I also made an LCD screen that will display the different game modes you're in. Game mode 1 is just a title menu. Game 2 is just a countdown that occurs when you actually push a start button. The third one just displays how many points as well as the lives you have in like a gameplay uh, display. And then the fourth one is just a game over display that shows how many lives and points you actually got for that particular round. I also wanted to create a game that increases in difficulty as you meet certain thresholds of points. This consists of 10 levels, starting, well, not including level 0, which is the one you actually start out on. At the end of every game, when you run out of lives, to start a new game, you just need to press the start button again, and the countdown will start over. This concludes my description of the actual game. We'll go into the hardware section next. This is the video for the hardware. My hardware was split into two sections, one for microcontroller, microprocessors A, and one for data conversions. I'll go through the data conversions one quickly right now. Pretty much each LED that I was using is turned on based on a range of analog values. These analog values are based off of an actual analog signal. The analog signal, the value from this analog signal is sampled until my logic clock actually falls to a low. When this occurs, it'll hold one value for a specified period of time, which is, again, until the clock goes high. This one value will be passed into an analog to digital converter. The values out of the analog to digital converter are, it consists of 8 bits. So 0 being the LSB, lowest significant bit, and 7 being the MSB, the most significant bit. When it comes out in the digital form, based on whatever the analog signal is being held at, I could have more than one high value, and we're trying to isolate one high value to turn on one of the LEDs. So if I put all these values through an 8 to 3 encoder and then a 3 to 8 decoder, I'll isolate one value. I used inverters because of the makeup of the actual encoder. It's looking for the most significant low bit, and the rest is don't care. So that means I'd have only one LED on for like half of my analog signal. So again, going through an inverter, I get out one high bit for any particular value along my analog signal. This value is then put through shift registers, and the shift registers consist of two phases. First phase, when it comes out, it turns an LED on. Second phase is when it comes out, it's looking to actually check whether or not you successfully pushed a button or failed to push a button. I have a diagram right here just to kind of show you guys what's going on. There we go. Let me adjust it perfectly right there, and it might take a little bit to see what my hands are doing. So we have 3 clock cycles, 1, 2, 3, right here. This is my clock, which represents that logic signal we were talking about. On the first rising edge, nothing happens. On the falling edge, one value is held by the sample and hold. And this value goes through the analog to digital converter. It goes through my encoders, my inverters, all that good stuff. And when it goes to the rising edge of this clock, so the second clock starts, that's when the output of my phase 1 of my shift registers, actually turns on and is kept on until the next rising edge of the clock right here. Okay? Whether or not you push the button is what comes out of the second phase of shift registers. Down here is the second phase of shift registers. If it's a 1, it means it's a fail, and if it's a 0, it's a pass. Again, after this LED turns on and we go to the next phase, this is just a random LED, and this phase goes on, and this next clock goes on and gets checked, another LED is going on, and then next clock, and it'll be checked, and then next clock, it constantly keeps going. So this LED might go on, and when it's being checked, another LED will be going on. That's the data conversions hardware section. That's cool. We'll move on to microprocessors hardware section right now. So pick 2 is my logic clock. The logic clock determines how long one of the LEDs is on for. At level 0, an LED will be on for 1.5 seconds. At level 10, an LED will be on for 0.465 seconds. What level you're on is determined by how many points you have. 0 points, level 0, and for every 10, level will increase. So level 1 is 10 points, level 2 is 20 points, level 3 is 30 points, all the way up to level 10, which is 100 points. At level 10, the clock will become constant, and the LEDs will continue to turn on every 0.465 seconds until you lose. Pick 2 takes an input from the second phase of shift registers. Again, when it's a 1, we'll know that you failed, and it won't increase that threshold of the levels. If it's a 0 from the shift registers of phase 2, then the pick will process it as you successfully push the button. It will increase your amount of points, and eventually increase the frequency, which decreases the period, which decreases the amount of time an LED is on for, again, until you get to level 10. It's also important to note that another input of pick 2 is an enable, and this comes from pick 1. Pick 2 will not decrease the period or start that kind of points count until it receives a low value for the enable from pick 1. This way, you don't all of a sudden start the game at level 10. That's my pick number 2. I'll be going into pick number 1 right now, actually. Pick number 1 outputs that enable based on you pushing the start button. So you'll push the start button. A program, it's programmed that after a certain number of clock cycles, 5, it'll output a low value for the enable, which again works for pick 2. Pick 1 takes in the clock from pick 2 and uses this to actually determine your score and how many lives you have. And pick 1 is in charge of the LCD's display. Again, pick 1 also takes in the phase 2 of shift registers, so it can determine how many points you have and lives you have to actually display it on the LCD. So again, pick 1 uses phase 2 of the shift to actually display what you have for points and lives. Pick 2 takes in from phase 2 to determine whether or not it should increase or just keep the clock at a constant level. That completes the hardware section for Microprocessors A. We will be moving into software for pick 1 and software for pick 2 next. This will be my software section for pick number 1. We use port C to actually display the different modes on the LCD screen, and we use port A as inputs and outputs from different parts of the circuit. I'm just going to go through the flow chart. You guys can't really see it, but I'll just talk loudly so you guys can understand what's actually going on. When pick 1 is actually powered on, so the voltage, the game's turned on, RA4 represents our start button. When it's 1, it's just going to display our title message. It's going to stay this until you actually push the start button. Just display the title message, which is nothing. Once you actually push the button, it will see a 0 at pick 1. And when it sees a 0, it'll jump into my delay, and it'll display a countdown message. This countdown message will just count down from 5 to 0, and you actually see it count down. It'll say, game will start in, and 5, 4, 3, 2. Once the delay is done, we go and we actually set RA5, which represents the enable, to 0. Again, when this is set to 0, it's passed to our pick 2, and the pick 2 processes this as, oh, it's low, so now we can start actually looking at the shift register 2. And the shift registers actually see a low, and they actually start processing data, which again will turn on LEDs and start looking at whether you hit them or not. So now we go into an infinite loop, and this just says while num lives doesn't equal 0. So it just means that your lives aren't 0. We go over here and we display the game. We display gameplay and the lives and points message. This will just display how many lives you have and how many points you have for the entire game, and the game is now going on. Right here, if RA3 equals 1 and RA2 equals 1, then we decrement the lives. So that means that the clock goes high, and we checked and we see that RA2 is high, which is the shift. It's the output out of the phase 2 shift registers. We'll see that they're both high. We'll know that, uh-oh, they missed their chance. They didn't push the button, so we'll lose a life. If it's a 0, which means we have RA3 equals 1, which is the clock being high, and we have the output 0, then it means you actually got a light, like you actually got a point. So you'll increment the points. Go into a connector, and then this just has while RA3 is 1. So while the clock is still high, it's not going to like increase your decrease your lives or increase your points. It'll just relax. As soon as it goes low again, we'll go back into the check if the number of lives is 0. If the number of lives isn't 0, we'll do it again. So we'll go through it. Once the clock is high, we'll check to see what RA2, which is again shift phase 2 is, and we'll go until your lives are equal to 0, and it will display how many points you actually have and how many lives you actually have. You run out of lives, we go over here. The enable button, the enable is actually set back to 1, which turns off all the LEDs and stops recording the clock. We'll go into a loop over here. It's just checking to make sure that the start button isn't pushed again. As long as the start button isn't pushed, we'll keep displaying the game over menu, which displays game over and how many points and lives you actually got. Once you push RA4 and it goes to 0 again, we'll get out. We'll go back to the countdown display message, and it'll keep displaying the countdown again. Game will start in when it equals 0. Enable RA5 is set to 0, and the game starts again. This will continue forever until you turn it off and turn it back on. That's the only other time you actually see the title menu. So when you turn it on initially, you'll see a title menu. From then on out, it's just gameplay, game over, and countdown messages. That is pick number 1. Now we're going to go on to pick number 2. This is the software section for pick number 2. I'm going to start off with a function that I use inside pick number 2, which is called determ half period. So it just determines the period. It actually determines the half of the period to be passed back to the main function. Half the period because it'll turn the clock on for this amount of time and then off for this amount of time, and that's it. So once the game actually starts, it'll just check the number of points you have. So right here it says if they're greater than 0, yes. Greater than 10, greater than 20, greater than 30, greater than 40, if they're greater than 50, if they're greater than 60, all the way till if they're greater than 100. For level 0, the period, I put the amount of time for the period because that's the amount of time the LED is on for, just on the diagram. You can't really read them, but I'm just going to go through them quickly. So level 0 period is 1.5. Level 1 is 1.25, 2 is 1 second, 3, 0.875 seconds, and then continue 0.75, 0.675, 0.6, 0.55, 0.5, 0.475, 0.45. Once this function is called and it goes through this whole thing, it'll just pass back a value, and that'll be the new amount of time that the actual clock goes on and off. Here's the main function for pick number 2. Pick number 2, when it's actually turned on, it'll initialize all my values, and it will go into this loop where it's just going to keep turning on the default clock on and off. It'll just keep turning it on because it's waiting for that enable. Once that enable equals 0, it'll start looking at shift phase 2 to determine when to increase the frequency, decreasing the period. Okay, so it'll keep going. You'll push the start button. Pick 1 will output 0 for the enable, and then we'll go into an actual loop. Okay, so while the enable is 0, it'll turn the clock off for half the period, based on determined half period, and then it'll turn it on for half the period. Then we'll look at it and we'll see that if shift phase 2 is high, we just relax because you didn't get the button. So we're not going to increase the period. We're not going to decrease the period on you if you can't handle the certain level that we're on. If RA2 is 0, then we'll increment the sublevel. This sublevel is past 2 half period, and that determines what the actual period is for the amount of time that the LEDs are on. After this function, we just go back in, we check the enable is still 0, and we continue to do clock 0, clock 1, clock 0, clock 1 until the enable is back to high. Once the enable is back to high, we just jump back up, reinitialize sub level, which is the amount of points you have pretty much, to 0, and we wait for that start button to be pushed again, and then the whole cycle starts over. That is pick number 2. Let's just pins real quick. RA4 output is the output for the clock of pick number 2, and RA5 is the input from the start button, and RA2 is the input from phase 2 of the shift registers. That concludes the software portion of my video. Now we'll just go into the demo. Hello, this is the demo. The sample and hold uses 15 volts, plus 15 and minus 15. Everything else uses 5 volts. This is my project. Here we go. D. Kinney, fall 2013, final project. Okay, so I will again just show you everything. Here's my whole game. This is just a signal generator that generates a 422 hertz analog signal from negative 100 millivolts to 850 millivolts. This is going to only turn on. This is only going to actually output my least significant bit from 0 to 5, because the most significant bits, the range of values is so high, it's just not a good. It won't randomize the LEDs being turned on well enough. So again, signal generator outputs a sine wave. Not part of the project, just want to use a kind of stable frequency that I can just turn on and off. Moving on, data conversion aspect of it with our pick controller, and then let's just get to the game. Here we go. So D. Kinney, fall 2013. Start button. I'm going to push it. It's right here. Start button. Okay, now we're going to start the game. Just by pressing the start button, you'll see it. Start game in 5, 4, 3, 2, 1. And the LEDs will start coming on, and I'll start playing with just 2 fingers. As you can see, we also have 12 lives, and the points will increase as I get correct wax of each mole.
I'm just going to continue to. There's the last LED. Okay, so now, as you can see, it's going faster and faster. But I'm not going to bore you guys with me playing Whack-A-Mole. So I will let myself lose. We can look at the lives go down 10, 9, 8. As you can see, the LED is still flashing. 4, 3, 2, 1, 0. It just says game over and tells you your score, 39. And then also, all we just need to do is just push the button again, and you'll see that it starts a new game. Start game, 4, 3, 2, 1, and then they'll go on. This concludes the demo and also the video for my Whack-A-Mole game and for my project for Microprocessors A and data conversions. I would also like to point out that there were two issues in my project. One of them was just the fact that sometimes an LED goes on for more than 1 or 2 or even 3 clock cycles. So you'll get a point for it and not even realize that another LED came on because it won't come on until it changes. And then the other issue was you actually have to push and hold a button to get a point. I didn't like that. I wish you could just push it and then move on to the next one. And that again, project. Thank you very much. Sorry about the length. Sorry about the lot of shaking, moving, all that stuff. And thank you very much. Bye.